Welcome to our t-test for two independent samples. We'll soon learn what that means for two samples to be independent, but we're still in our familiar t-test territory. The only major difference is that now we have two means that we're testing against each other, two sample means, and we'll find out how independent samples are different from, in the future, we'll discover what dependent samples are, but that's not for this case. Today we're talking about two independent samples, and we're still using the t-test framework that we've been building up in the last chapter or two. And of course still using what we know based on probability and making judgments about statistical significance, and also thinking about the difference between statistical significance and effect size. So all that and more coming up. So you can see our basic overview of what we're going to cover today. Basically, these things are going to look very similar for the next few slideshows, because we're going to do the same basic layout, the same key milestones that we need to cover for each test. So each test is basically going through the same rhythm, except with a couple major exceptions or differences in terms of the type of test we need. But the basic process is the same. We just have to think about what is the starting conditions of the data to decide which test we need to lock into and which is appropriate to do. So first we're going to look at an overview of a hypothesis test with two independent samples. And it has to be two. It can't be less than two or more than two. For the t-test territory, it has to be exactly two. We'll find there's other options in the future, hint, hint, analysis of variance, that can also do this exact same analysis. But if we have two independent samples, the simplest, most direct way to do that analysis is t-test. So what we've been looking at before is what we call a single sample technique, and this is our z-statistic and our one sample t-statistic. And of course, if we're going back in time, what's the difference between our z-statistic? Well, we have a known population mean and we have a known population standard deviation. We had to move into t territory when we didn't have a known population standard deviation, and we had to estimate a standard error for our population. So again, t time or t statistic time is when we don't know our population standard deviation and we have to estimate it. Now, a lot of the things that we're going to consider, a lot of the questions that we want to answer involve more than one sample. So again, today we're starting in that territory, and we see some examples of that. Do Caucasians and African Americans differ in their approval regarding president's response to insert whatever big hurricane unfortunately happens every year, or sometimes multiple hurricanes that do major damage? And then there's also, when that happens, usually a public referendum on how well the response was, how effective it was, whether it was affected by the president's or the people the president had put in charge of FEMA and other relief organizations. And so we look at one group compared to another group. Now notice you can't be in both groups. This is what is effectively the difference between an independent sample and other types of samples. Independent means you can only be in one or the other. It's not a before and after. It's not about change. It is, if you're in this group, are your responses different to people in a different group? So oftentimes we look at racial ethnic status, as here. Also gender, Ohio State versus Michigan fans, Democrats versus Republicans, Americans versus Canadians, all sorts of, you can only be one of these categories, and we have a mean for each of them. Are they different? Now, compare that to here. Does watching a 60 minutes expose on the approval change based on a before and after? So here is not independent. This is a dependent sample because it's the same people who are looking or providing their responses before and after, and now we're just looking to see if that has changed. But again, we can still stay in our basically t-test territory. It's just this is up here an independent samples t situation, and this would be a dependent samples t, which we'll cover in a further slideshow. So a couple things to keep in mind, we have some terminology that is somewhat interchangeable, and that it would be appropriate to use these descriptors in research that I see published in ways that I describe it too. So it's just important to keep us all on the same page regarding terminology here. So, for example, we have our same examples here: independent samples, dependent samples. Typically, if we're talking about the analysis, t-test, we often use the independent versus dependent phrasing. Whereas if we're talking about the study design, we talk about a between subjects for an independent samples or independent measures even, or a within subjects design for the dependent, sometimes called repeated measures even. So it's important to realize there's more than one term or phrase that can describe the same thing, but it's important now to see how these kind of go together. Independent, between, dependent, within. So again, we'll come back to these repeatedly, but let's start to get clear and precise on our terminology right now. So let's look at the overview of what we're doing. Already talked about how the progression is leading up to where we are today. So again, with our z-test and our one sample t, we just have one sample and we're comparing it to a known population mean. So you can see, yes, we know the population mean for what we've covered before today. And of course, the only difference between our z-test and our one sample t is that we did know the population variance for our z-test, but did not know it for our one sample t-test. The independent samples, now we have two samples, and we don't know a population mean, but we really don't need to for reasons we'll see coming up. We just need to compare our difference between our two independent samples. And of course, it was nice to know the population variance for our z-test, but really there's no going back now. Basically, any test that we're going to use in the future are using conditions or having to deal with conditions where we don't know the population variance. And we'll talk about today in a little bit. How do we estimate population variance? We have to do something known as pooled variance. So let's look at the beginnings or the foundation for the independent measures research design leading to independent measures hypotheses and so forth. So let's be precise on notation. If we have a sample size, we are talking about little n for sample 1, little n2 for sample 2. We have our means, which is big M and big M2. And for each sample, we have also a measure of variability. In this case, our sums of squares for sample 1, sums of squares for sample 2. We also look at our hypotheses. Basically, we phrase our hypotheses in terms of the population means because that's what our research question involves. We don't care only about our sample data. We care about using our sample data to infer or make conclusions about what we think is going on in the in this population. Of course, the problem is we don't have our population parameters, and so we have to use our sample data or statistics to make inferences about the population. So of course, we're thinking, when we think about our hypotheses, about the population, and that's how we phrase our hypotheses when we write them out using notation. So we have two basic hypotheses. One is that take our two population means, again, males versus females, Democrats versus Republicans, and there's no difference. That is our null hypothesis. We can also phrase it the same way, they're equal, or just the difference between them is 0. These are equal ways of phrasing this. So usually we'll just go with the simpler one. And then the alternative hypothesis says that there is a difference. So this difference is not equal to 0, or these two means are not the same. That means there is a difference, it is statistically significant, and we can conclude that we reject that null hypothesis of no difference if we look like we see a meaningful difference. And notice this is a not equal. We're not using a greater than or less than sign, so this would be a two-tailed or non-directional hypothesis. So now let's introduce our statistic. So basically our t is pretty simple. We're just taking for our single sample t-statistic, so this is the one we're already familiar with before today's lesson, our sample mean minus our population mean over our estimated standard error. What's the independent measures t-statistic? We have our sample mean 1 minus sample mean 2 over, well, we can see how the S with a subheading of M is a estimated standard error, just like it is in the previous t-statistic, but now we've got a little bit different notation here. So we'll see what that means and what that's about in a little bit. We also have our population mean, 1 and 2. The idea is we don't actually know this, but we put it here in our initial version of the formula just to basically state that this is what we're trying to figure out, but we don't have these values. So essentially, when we use the t-statistic, we don't have population means, so this basically drops out to 0. So what we're really concerned with is this difference, our two sample means, over our estimated standard error. So basically we have the three components, our numerator, the mean difference, and then we have our estimated standard error, which is, oh, we're getting complicated here, but it'll make sense when we break it down. We've taken our pooled standard deviations, and since we have that for two samples, we have two components to this equation that's eventually going to lead to our denominator, or this bottom part of our independent samples t-statistic, and otherwise think of it as our error term, our noise in relation to our signal, which is the main effect we're testing. And of course, we want this error to be low. If this is low, our mean difference is going to look bigger. Same mean difference, if this is high, our error is big, our t-statistic is smaller. So let's think about a little bit more about standard error. Basically, there's a difference between sample means, that is our effect, not error yet. But if we think about sampling error, again, we don't know our actual population mean and population mean for our two populations. Again, males versus females, Democrats versus Republicans. We are just inferring that our means that we got, our sample means, are somewhat close to our population values. But of course, sampling error means whatever sample mean we get, we don't assume it's going to be exactly the same. So the same inferences or kind of guesses that we make that from before have always applied. The bigger our sample size, the closer we think our sample mean is to our population mean. So sample size usually gives us more confidence that there is less standard error in terms of sampling error specifically between our sample mean and our population mean. But this time we have two sources of error because we're drawing from one population to get our first sample mean, drawing from another population to get our second sample mean. So we have to include that into our error term or our denominator. Now you might just think, well, let's take our basically standard deviation for sample 1, standard deviation for sample 2, divide it by 2, and then we've got our average. But remember, if those samples are not equal, and there's no reason they have to be, we don't have to have equal number of males or females. We probably want them to be kind of close, but they don't have to be exactly the same. But if they're not exactly the same, then we have to account for that, well, the bigger sample is going to have more pull on the overall standard error. Just like with a weighted mean, if we're trying to average the mean of two samples and they have unequal sample sizes, then we have to do this weighted mean formula rather than just the simple divide by 2 average. So that logic is what leads us into this pooled variance idea. So basically, we need to come up with one measure of variance but we have to average it from two sources, sample 1, sample 2 of variance, or variability specifically. So for example, we have our sum of squares for sample 1, sum of squares for sample 2, and our degrees of freedom for sample 1, degrees of freedom for sample 2. Now so that's when we're looking at our pooled variance. And since it has a squared term here, we know it's variance and not standard error yet. Well, how do we go backwards when we're looking for a variance? We got to go backwards to our sum of squares. So again, this is just things, especially sum of squares. Remember, on our way to calculate standard deviation, we have to do deviation scores, and then we can get our sum of squares, and then we can calculate our variance, and then eventually our standard deviation. We just have to do this twice now because we have two samples. So let's say we apply this formula. We have our sums of squares for sample 1, degrees of freedom for sample 1, sums of squares for sample 2, degrees of freedom for sample 2. Now we just add them, and then do the division. Then we get our pooled variance, and we pop it into our estimated standard error. And basically we look at this subheading here for our estimated standard error, which is we have a mean 1 minus a mean 2. So it's basically just saying that this is a independent samples standard error. So hopefully that is clear, that even though we got a lot of notation here, all it's saying is that it is a standard error. The bottom of our t-statistic, the denominator of our t-statistic, for an independent samples, one mean minus another mean from sample 1 compared to sample 2. Another way to think about this, these are just different ways of thinking about the same basic issue that we're trying to tackle. So our t, if we put it in words, we have our sample statistic, and again, our hypothesized population parameter. We don't know the actual population mean. All we have is our two sample means that we're comparing over some sort of error term. In this case, a better way to phrase it for me, especially in the numerator, would be two sample means. What's the difference between them over our standard error? And notice that now we're into t level. This population mean is just going to drop off to 0. Functionally, for the math, all we need is this sample mean 1 minus sample mean 2 over our estimated standard error. And if we want to work backwards, this is our formula for the estimated standard error, going back to our pooled variance. But these equations are essentially equal. This one we've just combined more work into this term, where this time for this error term we've just worked backwards to the previous formula to calculate that error term. Or once again, compared to our single sample t-statistic, we go back to degrees of freedom, n minus 1. But as we're going to find out in a little bit, now we're going to have n minus 1 for sample 1, n minus 1 for sample 2 in terms of our degrees of freedom. And again, we have our sample mean, we have how we're phrasing our hypotheses, what we think the population means are, but we don't have these actual values. So we just have to rely on the means we do have as an estimate of that. And of course, we have to have an error term or denominator for our statistic. And so previously, we could just do, for our single samples t-statistic, our sample variance. And how did we get that? Sum of squares, degrees of freedom. And now we just have basically double of both of those. And of course, we have different sample sizes. And even if we do have equal sample sizes, we're just going to go ahead and use this formula anyway for our pooled variance. So we have our pooled variance, which is our averaged variance, and we just divide that by our first sample, divide that by our second sample, and that gives us our pooled variance term. So now let's look at this, what we know about the pieces of our t-statistic formula, and basically put them together within our hypothesis test framework. So first of all, as we've covered before, we have our null hypothesis and our alternative hypothesis. Null saying there is no difference in the populations. Population 1 minus population 2 is 0, whereas our alternative is that there is a difference, and again, this is a non-directional or two-tailed test as phrased here. So next we go for our decision criteria, which hopefully is starting to feel fairly familiar by now. We select an alpha value, choose if it's directional or non-directional. We have to figure out that degrees of freedom, and then we have to think about our critical regions, and we have to, for this, use our tables at the back of the book for our, in this case, still using the t-table that we introduced previously for the one sample t-test. That table is still fine to use for the 2 independent samples that we're covering today. Then all we have to do is apply these formulas. A couple quick things to keep in mind. What I want you to know at this point is basically, what do the formulas mean? What does the numerator mean? What do the symbols mean? Can you explain it? Can you see the difference between sum of squares versus variance, and which comes first in the steps, the order? But I'm less concerned about putting them all together to solve from start to finish one whole problem. I just want you to be able to look into the different steps and be aware of the notation involved at each step in terms of exam questions and things like that for this class. So I'm looking at a conceptual understanding, but not having to apply necessarily all these formulas at once, although we will work through a problem from start to finish. So let's look at some assumptions underlying the independent measures T, process, formula, statistic. I interchange those in this case. So first of all, we have 2 samples, and now we have some considerations involving those 2 samples that, again, these are assumptions. That means that here's situations in which it's appropriate to do the test. So we have all sorts of assumptions when we're going about daily life. When we turn on our car, we assume there's gas. When we turn on our car, we assume that the gas isn't contaminated. We assume that nothing bad has been added to that. So the same thing for these statistics. We assume that everything is how we expect it, but we can't just pretend that it is. We have to spend some time thinking and maybe looking around to determine whether it really is. So for example, since it's an independent samples t-test, we need to make sure that the samples are independent. So what this means is that you have to have 2 groups, and participants can only be in one or the other. So for example, if you have somebody in your Democrat group who's the same person in your Republican group, that violates this assumption. So each person can only have one observation in one group. So no before and after, no same person in both groups. They have to be different, they have to be independent. We also assume that the populations from which the samples selected are normally distributed. This maybe we just want to look at our graphs. For example, we can look at we can use our statistical analysis software to just look at the shape of the distribution. Are most of the scores in the middle with few outliers on either the positive or the negative end? And then we have what's known as this equal variances or homogeneity of variance assumption. So homogeneity means similar, which means that we don't want to have our male population have a ton of variability, a very wide distribution, and our female distribution be very narrow. They need to be fairly similar. General rule of thumb might be if one variance is 3 or 4 times larger than the other. So really, we just want to look at our variance for sample 1, sample 2, and see if they're not gigantically different. Although, if this is still okay, 3 or 4 times difference, this is what we call a pretty robust assumption, meaning you have to have a big difference to be considered to have violated it. So in most cases, I'm not going to be too worried about this violation of the homogeneity or similarity of variance assumption between our two independent samples. Now this is less for us to actually do, but you can have some tests depending on which book you're using. Some courses I teach, we don't have these more detailed options in the back, so this isn't for exam purposes for any of these details on here. But there are some ways, if you're concerned about your homogeneity of variance and if you violated that assumption, there's what's called an Fmax test, again, not for exam purposes. And basically, instead of just guessing, oh, 3 or 4 times, I guess, maybe I'm starting to get worried, but should I really be worried? Having the actual test will tell you, yes, you violated the assumption, no, you haven't. So in some cases, you may really need a test like this, but basically, for our purposes, you look at the variability of sample 1, variability of sample 2. If they're pretty close to the same, you don't have to worry about violating the assumption. And if you are worried about it, there are options to get a definitive answer such as this, but in most cases you won't have to. It's just out there as an option if you'd like to use one and have more certainty or confidence saying that you were worried about violating the assumption, but this test shows you didn't actually violate it. You're good to go. Keep using your data. So let's also look at the effect size for the t-statistic. Basically, we have our 2 different ways to think about effect size. Once again, we have our percentage of variance accounted for, or R squared. But for our purposes, we're going to mainly just focus on the Cohen's d, because we're already kind of familiar with that, what a big Cohen's d looks like or a small or medium one looks like. The only thing now is, again, for our t statistics or even our z statistic, we have our mean difference, the effect, that's the same as our t statistic, but instead of doing our estimated standard error, which is always going to be small standard error with a big sample size, big standard error with a small sample size, we go a step back and use our pooled variance, which is a little bit less tainted or affected by the sample size. So that's how our effect size is different than our t statistic. It's less biased by our sample size because we're going back to our pooled variance or standard deviation. And of course, if we think about the variance accounted for, essentially there is a way to incorporate our actual t statistic. So the bigger our t is, the bigger our t statistic result is, the bigger the effect size is if we want to look at variance accounted for. But basically, for our purposes, we're going to use Cohen's d for the go-to effect size for our independent measures t statistic. And finally, let's look at APA style. How do we report our results with the independent samples t statistic? Basically, we want to include the descriptive statistics, mean, standard deviation, but of course we have 2 groups. So mean and standard deviation for group 1, and then mean standard deviation for group 2. Again, these are just the descriptive statistics. We see there is a mean difference. It looks like using mental images results in higher recall, a higher mean of recall in words than not using mental images, probably some sort of instructions of how to use these mental images versus no instructions. And we see there's a mean difference, but is it significant? So then we need our t statistic, and we can see t of, in this case, degrees of freedom of group 1 plus group 2 is 18. So how many people were in the sample? Well, sample 1 would have n minus 1 for degrees of freedom. Sample 2 would have n minus 1 for degrees of freedom. You add them up to get 18. So working backwards, the sample size for this had to be 20 for example. We see the t is 3 with a p-value alpha of 0.05. That means there is a 0.05 or 5% chance that we've made a type 1 error, 5% chance that we've said, look, this is significant. Our t is greater than our cutoff value from our t-table, so we conclude that yes, there's a significant difference between these two means. We also see but there's still a 5% chance that we've falsely rejected, or we've made our decision and our decision was wrong. Our 5% chance, that's our alpha value. And then if the difference is significant, it's appropriate to then report the effect size. And we can see the d is over 1, so it's definitely a large effect. So this difference is significant, the difference is real, and the difference is also considered large. Now also, did the critical region fall in one or two tails? It's not completely clear. The phrasing, we say there was a significant difference. So probably we would say it was a two-tailed test. If they'd say a one-tailed test was used, usually we would like to see that reported. So the default assumption, if we don't have any more information about one or two-tailed test, directional or non-directional, if they don't say we used a one-tailed test, we assume they just use a two-tailed, and that's how they got their conclusion of significance, by using the cutoff or the critical values for a two-tailed test. So a quick review as we wrap up. True, false here. You'll be much more likely to detect a treatment effect when the estimated standard error is large. This is false. The denominator is, when it's big standard error, that makes for a smaller t-value. We want a small standard error, which gives us more power. More power, more likelihood to detect a treatment effect, more power for a small standard error. So this is false. Homogeneity of variance between the two samples states that the two variances must be equal. No, they don't have to be exactly equal or even that close. They just can't go too far different before we question whether this assumption has been violated. When pooling variances, the value will be close to the variance for the smaller n. Well, just like with the weighted mean, the mean with the larger sample size will contribute more to that weighted mean. So in this case, this is also false. It's actually, the pooled variance is more influenced by the sample with the larger n. Increase in sample variance will produce an increase in value for t. Again, where's the variance in our t-statistic formula? That's in the denominator. So a increase in our denominator makes for a smaller t-statistic, so this is false. A decrease in sample variance, however, would produce a higher value for the t-statistic. And if that doesn't make sense talking about it, go back and look at the formula, because it's right in there for the answer to get for this true-false. Also, t of 6, 1.98, probability is greater than 0.5. This means there's a greater than 5% chance we've made a type 1 error. So this would have to be probability of less than 0.5 for us to reject the null hypothesis. So if this is reported this way, we say, no, null was not rejected. We can only conclude a significant difference if the probability is less than 0.5. Or if we choose the even more restrictive alpha, 0.01 or 0.001, the probability of type 1 error can't be larger than that. It has to be that or only smaller. So this, again, is false. Okay, so a researcher reports t of 24. And here's our t-statistic. How many individuals participated? Well, we know our sample 1 had to be n minus 1. Sample 2 had to be degrees of freedom equals n minus 1. So basically, this 24 is n minus 1 minus 1. So that means if this is our degrees of freedom, then we have to know our sample size was 26. We don't know how many were in each sample. All we know is that n minus 1 plus n minus 1 equals 24. So working backwards, our sample size has to be 6 if our degrees of freedom, or 26, excuse me, if our degrees of freedom is 24. Again, this would help if you look back at your equation to know for sure. But for our pooled variance equation, we take our sum of squares, sample 1, sum of squares, sample 2, add those together in our numerator. So we already know it's got to be 50. But again, we're taking an average. In this case, we wouldn't have to do the pooled variance formula because the sample sizes are equal, but let's assume we did. So again, pooled variance, do we use this? Do we use n? No, in fact, we're using degrees of freedom for our pooled variance. So we do n minus 1, 5, plus n minus 2, 5. And so C would be how, once we plug in the values, what our formula for our pooled variance would look like. Which of the following studies would be an independent samples design? Remember, it has to be one group compared to another group. You can't be in both groups. So it can't be a change, it can't be a before and after. So in this case, change after 4 weeks, before and after, not independent. Before and after, not independent. Age 2 versus age 3. This could be phrased a little bit more clearly. But basically, the way this is phrased, I'm thinking this sounds like I could do this better. This seems like change, the development of. So how is it changed from age 2 to age 3? The best answer here is the difference between verbal skills between 3-year-old boys and 3-year-old girls. So a bunch of 3-year-olds, but we have one sample of the boys, one sample of the girls. This is the clearest independent samples study design. And finally, the null hypothesis. First of all, we only have sample means, big N's, for our formulas, but our hypotheses are not just based on our sample statistics. We're doing inferential statistics, so our hypotheses are phrased at the population level. And the null hypothesis would say that take one population, subtract the other population mean, and we get 0. If there's no difference, this is our null hypothesis. And of course, we want to reject this null because we suspect that the alternative hypothesis is more likely closer to the truth. So anyway, hopefully that was helpful as we think about our increasing complex research and statistical design. We have more information, 2 means, and of course with those 2 means, our independent samples, we have corresponding standard deviation and sample sizes for each of those independent samples. So the math and the formulas get a little bit more complicated, but hopefully the underlying logic of how we apply this t-statistic, you can see at least that hasn't changed much from the one sample's t-statistic. So again, looking forward to discussing this and seeing your thoughts, and hopefully this was helpful in advancing our journey in the t territory.